Hello and welcome to the CSES Algorithm Problem Solving Club Meetup today. We have a new problem. It's called the grid paths. If you can hear me fine, please post a message on chat so that I know my audio system is working fine. We'll first go through the problem statement, and then thank you Traxxas for the confirmation that the audio is working fine. So we'll first go through the problem statement, and then we'll read a few pages of the book which talks about a problem like this. It has some helpful optimization techniques, and those optimization techniques were indeed useful to me as well when I was writing this solution. So let's see the problem first. There are 8 paths in a 7x7 grid from the upper left square to the lower left square. So if we start from here and we end here, so upper left square, lower left square, so this is saying that there are 88,418 paths that can go from here to here, such that each, okay, where is the constraint? I mean, there's a constraint that we're not supposed to go over the same cell twice, so there should be no intersections. That's one of the requirements. I think it will be coming somewhere. Let's just go through it. So each path corresponds to a 48 character description. Yes, so it is 48 characters because there are 49 cells here, 7x7. So there are 49 cells, and we are already, so we can think, if we think of it as like a single player game where we are making moves, so we are already on the first cell when we have not made any moves at all. When we make the first move, we have come here. So we have consumed 2 cells. So with a single move, we have consumed 2 cells. With 2 moves, we will consume 3 cells, and so on. So to consume all the 49 cells, or the right word would be visit, to visit all the 49 cells, we need 48 moves. So those 48 moves would be represented as characters D for down, U for up, L for left, and R for right. For example, this specific path, and this is just one of the 88,000 or so paths, this path corresponds to this string. So this is the encoding of the path taken by this single player. For example, let us see. So we'll just check the first few characters. So D, R, U, R. So D for down, R for right, U for up, R for right. And there are more R's, and then so on. So given a description of a path which may also contain, and this is the twist. So this, what we had so far is a normal grid path search problem, but here we have a twist. And once again, I would, like if this is the first time you're seeing this problem, I would recommend that you focus on the grid search problem first, and then latch on this twist later. And the twist is, you are given a description of a path which may also contain characters ? Any direction. Your task is to calculate the number of paths that match the description. So you could think of it like a pattern, a path pattern already given, and how many paths out of this 88,000 paths match this pattern. That could be one way of describing this. So for example, does this one match this pattern? So let us see, TRU, and there are 6, and then 1, 2, 3, 4, 5, 6, probably does. So yeah, it looks like it does. So so of all the possible paths, we need to only count those paths which match this pattern. And this is again a small twist. It's not a very, it doesn't cause a lot of difficulty in the solution. Understanding the grid search itself is the main, I would say, the main essence of this problem. And this little twist can be added later, even in a retroactive fashion, without much trouble. So we'll go through the book now. That's what I've planned for the day. And once again, I'll show you where in the book this thing is, because we have been following the book in a linear fashion so far. But this is the first time I'm jumping ahead to a section. But this section is fairly self-contained. So even if you've not read the previous chapters, it isn't. This section will still be pretty easy to read. So this is the section. I'll just go from top. So say we are at the top of the book. We open part 1. We open complete search, which is chapter 5, and within that, pruning the search. So this is where we will be going through some of the optimization techniques, not each one of them. Okay. So before I do that, let me come back to the code and show what a grid search even looks like without optimizations. I have the optimizations encoded in this code, and there are two levels of optimizations. There are algorithmic optimizations, which will get from a very poor algorithm to a good algorithm, and then there is micro optimizations. So that is the C++ optimizations to make the code more efficient. So first, we will learn without any optimization, no optimization at all, and see what the algorithm looks like, which means I will ask you to ignore some part of the code as we go through this code. All right, so this is where it begins. Here, solve. And I write the code in a slightly atypical fashion, meaning I pass every single parameter in the interest of good software engineering practice, but most people don't do that. Most people put all this reusable stuff or this stuff that we share between function calls as global variables, and that is perfectly fine. It's just that I like to pass them unless really necessary to put them outside in global. So that's why you see so many parameters. I'll focus on the important ones first. So this is the solve function. This is a grid A. So this is a two-dimensional grid. We can also think of it like the visited matrix. So this will tell us which cells have been visited. This is our scratchpad. Just like in the nth queens problem we used a scratchpad, this is the scratchpad, this variable A. Probably a better name would be visited, because this keeps track of which cells have been visited. It's a lookup table for that. This is the cell that we'll visit now, I comma j, where I is the row number, row index, and j is the column index. So this tells us which cell we are visiting now in this current call. Move num, this is the move number. Is it the 0th move? Is it the first move? Is it the second move? It will take care of that. And this is the path that has come from this input. This is what I'll be saying. If you're really new to this problem, I would say ignore this detail for now and focus on just the grid search. This is where we'll count the result, and as you can see, I'm passing it by reference. So we could have as well made it global variable, but I'm just passing it by reference so that I can keep updating this. Of course, there are other ways to write this. One could return the count from the recursive call. That could be another way, but I'll just show it this way, where I'm just passing this result to every call, and every call has a reference to this result. It just does a plus plus to this result to update it whenever it finds a solution. Solution meaning a path that satisfies these constraints and ends up here. Okay, now let us see how we start. We say that we start with a blank slate, which is this one, a blank scratchpad. Every cell is available, no cells have been visited. And we say solve it for 0, 0. So which means we are here. So the first call is telling this solve function that we are here at this top left corner cell, and then start the search. This 0 is move number, so we have not made any moves yet, so that is move number 0. Or you could say just placing that player here is the first move, and this is the result where we'll count. So it's initialized to 0, and we'll keep doing plus plus to this. This is the recursive backtracking algorithm. It's just I would say it's just a fancy name for something that is, I think, it's almost like common sense. So say we want to, if as a human, we want to figure all these paths out, what would we do? We will place the player here and then try this path and then try the right path. Yeah, those are the only two possibilities. And then for each one of them, we'll try all the other possibilities. So when we come here, we try the right path and again the left path. When we are here, we try the left path. Okay, we can't go back left because that is already visited, but those are the checks we have to do in the code. And then we try the right move and we try the down move and so on. It's basically just going deeper and deeper into a recursion stack and exploring all the possibilities with this as the starting point. So let us focus on that. So if we did not have this detail, this specific thing, the code would look like this. And let me just edit this on the fly just to show how simple it would look like. Yeah, probably something like this. Maybe I'm making some mistakes while editing it live, but this is the essence. This is what the code would look like. And let me see if I can also, let me also indent this properly. Yeah. Okay, so all these cases I'll explain later. Some of these are also optimization cases, so that I'll explain later. So just focus on this. Just imagine that these things are not there for now. Okay, and I'll bring them back one by one. So this is what the essence of the solution is. We will occupy the cell, the current cell, which is ij, beginning with 0, 0, and then we explore every possible movement. So we say solve it for, so move the player on the, so this is going which side? This is going I minus 1, which means go up. We're reducing the row number. So move the player up and explore solutions. Now, obviously, this is invalid when we're just starting because on the up there's nothing, and we have to do those checks. And those checks will be something I'm hiding for the sake of simplicity, but I'll bring those checks back. The next thing we are saying is that with this as the starting cell, go. So I'll call this moves. So this down, up, left, and right, I'll call them different moves. So this is saying do a down move and then continue solving. So this is the down move where I'm incrementing the row number by 1. And similarly, a left move, in this case, it will be invalid move, and the right move. And this is the essence of the solution. So this is the recursion. Now, of course, we have to take care of the base case and some of this invalid cases where we are going beyond the grid. So let me bring up some useful code back and see what we need to see. Okay, so the base case is here. This we can ignore for now. Okay, so I'm not removing that because otherwise my undo stack will become deep in this validating on this in the Emacs editor. So I showed this much. Yeah, and one more thing. So here we are setting it to true, the current cell, because when we go in the deep into this recursion and we're exploring other cells, those deeper function calls need to know that this cell is occupied, so that it doesn't select a path that intersects the cell again. That's why we're setting it to true. And once we have explored all those paths, we're setting it to false to free it up. And this makes a lot of sense if you think about somewhere deep in the call stacks. Let us say in the first call we selected down, in the next call we selected up, and say we are here. So the previous two calls have already set this to true and this to true in the scratchpad. So when we are roaming from here, we should not be selecting this path again, and that check we have to do. And again, when we come back, we need to say we have come back from here to here. Okay, we have explored everything here and we've gone back to this call stack. So before going back, we need to free this up again so that this player can again explore other sites. So that's the idea. I don't think I did a very illustrative description of that, but if you just think about it, it should make sense in case you are seeing it for the first time. But most people here, I know I've solved this before, so I'm pretty sure this already makes sense to you. So here we occupy the cell. Here we say that we are freeing up the cell. We don't occupy that cell anymore. So that we go one stack, one caller up, and then it can explore other paths. Okay, now how do we take care of all these edge cases? So this is that part. If I is -1 or I equals n, which is beyond here because this is from 0 to n minus 1. Assuming capital N is the size of the grid. In this case, it is of course 7. So n minus 1 is 6 and n is 7 here outside. So if I is n, then we are outside. If similarly for j, if j is -1, then we are in, okay, maybe I'm pointing the rows and columns wrong. So I is the row number, right? So I equals -1 means we are here on this row. If I equals n, which means we are outside here. So those are invalid and we just return. So this is where we start abandoning searches, because once we have gone outside the grid, there's no more point in continuing. We just start returning. We don't solve recursively. So those become some of the base cases where we start returning. And similarly for j, the column numbers. And then continuing, other thing we need to check is if the cell is visited already. So if by this recursion, while searching, I land on a cell that has already been visited, which is looked up here, then we should not step on it. We can abandon that direction of search and just return. So this is the if condition, to the if statement to take care of all those cases where we can start returning. Okay, so that is the essence of the solution. And when we do this thing, we would have explored all the possible searches and got the answer is 88418. But obviously we don't have, we are not going to search all possible paths. We will be searching only those paths that match this pattern. And for that, we have that additional code that I had before. Let me bring them back. Yes, so now I can explain this. And these are optimizations, what is present here, which I have to discuss a little bit later. So here we are going to check. So this is the movement, this is the up move. And when can we make an up move? So here we are picking up the move. What is the current move from this path? And this path has been read in the main function. I'll just show you here. String path, and I've read the path, the entire path. Now we are at move number 0 when you're beginning. So we're checking here from move number 0 to move number 1. So this is that move. This is saying that how we go from the 0th position to the first position, the first move. So this is question mark, which means all 4 moves are allowed. And you can see that is what this is doing. When move equals question mark, we are doing this. When move equals question mark, we are doing this as well. When move equals question mark, this as well, and this as well. But say we have explored some of the paths and we come here. We are on the, what is this, the 7th move. And we look up the 7th move and it says only R. We are only allowed to do R. We're not allowed to do question mark, which means all the paths, all the moves. Then we just hit this one. So this, if you see this if statements, each of this will execute on question mark, and or it will execute only when the specified path is mentioned. So if in this case, it will not match this, it will not match this, it will not match this, it will match this, and only execute exploring the next search, the next level of search by doing a right move. So that is all. So that takes care of the twist, and that is all there is to this twist that has been added to the basic grid search problem. Okay, so that completes the description of the basic grid search problem without any optimizations. Now we'll go through the book to learn some of the optimization techniques. I will not go through each one of them because we will be going through this book later when we come across this chapter in a linear fashion. I will just go through those optimization techniques that are useful for this problem. So let's start from here. We can often optimize backtracking by pruning. I'll just close this sidebar here. Yeah, we have more space. Okay, yeah. So we can often optimize backtracking by pruning the search tree. The idea is to add intelligence to the algorithm so that it will notice as soon as possible if a partial solution cannot be extended to a complete solution. Such optimizations can have a tremendous effect on the efficiency of the search. Okay, so let us consider the problem of calculating the number of paths in an n cross n grid from the upper left corner to the lower right corner, and it's a slightly different problem, but it's just an implementation. I mean, it's just a tiny detail, like where we want to start and where we want to end. So here we want to start here and want to end here, but in the problem being discussed in the book, we want to start here and end on the bottom right corner. So, but the concept that we'll learn holds good, no matter where we want to start and where we want to end. So, for example, in a 7 cross 7 grid, there are how many? This is 111,712 such paths. Here we only had 88,000, so there are more number of paths. I'm going to go from here to here. We focus on the 7 cross 7 case because its level of difficulty is appropriate to our needs. We begin with a straightforward backtracking algorithm. And that is what I've explained so far, the straightforward backtracking algorithm, where we just visit a cell, and from that cell we explore all the moves. We perform all the moves from that cell. Okay, so yeah, and then optimize it step by step using observations of how the search can be pruned. After each optimization, we measure the running time of the algorithm and the number of recursive calls so that we clearly see the effect of each optimization on the efficiency of the search. Basic algorithm. The first version, which is what I explained so far, takes these many seconds and these many billion recursive calls. That's fine. Now optimization 1. Okay, this I will skip over. If you're interested, you can read. This is not important for today's study, so I'll just skip over this one. That explores the symmetric nature of the moves, which holds good if you're going from here to here. Okay, this is important. So if the path reaches the lower right square before, so I will not say lower right square because our target is different. I'll just call it target or destination. If the path reaches the target cell or the terminating cell before it has visited all other squares of the grid, it is clear that it will not be possible to complete the solution. So if we just go from here to here directly, say we are exploring, the recursive calls are exploring a path like this, where the first move is down, the second move is down, third move is down, fourth move is down, fifth move is down, and sixth move is down, we know it's not a solution because we are supposed to reach this cell in the end after having visited everything else. So that is not a solution, and we can terminate that search there. So we can start returning from there so that we don't go and waste processing time exploring other cells when we already know that we have stumbled upon a case which clearly shows that we don't have a solution. So that is one optimization technique, and this, I guess, is a very obvious optimization technique. I mean, we don't need, I don't think this really requires a book to teach us that. It's very obvious, very easy to realize while writing the code. And let me show you this part first. So that is the first optimization technique, the first pruning method. So what we're doing here, if I equals, so this is the target cell, is checking that. So if I equals n minus 1, meaning we're at the last row, and j equals 0, meaning we are at the first column, so it is this cell. We have reached the target cell. We are checking, have we reached it too soon? With the move numbers, and how many moves are expected? N times n minus 1. So in this case, it is 7 times 7, 49, minus 1, because there is one move less, like I explained in the beginning. Because when absolutely no moves have happened, the player has already visited one cell. So that's why there's one less. So if we have reached the target cell in less than the necessary number of moves, we can return. There's no point in coming here and doing a deeper search because we don't have a solution. This is an invalid solution case. But if we have reached the target cell, which is this condition, with the correct number of moves, so we reach this else part. So I'm not writing the else because it's written here, but this essentially is the else part, and we count that as a path. So we do a result plus plus. Now we know that we counted one valid solution, one valid way to reach the target cell, having completed n times n minus 1 number of moves, or 48 moves in this example. So that is optimization technique 1. Okay, 2 in this book, but the first one that we're discussing right now. Now 3, and this is a very interesting one. And this is where the book did help me to understand these optimization techniques. So if the path touches a wall and can turn either left or right, the grid splits into 2 parts that contain unvisited squares. So just take a look at this example, this illustration here. If we end up here like this, now there is no way we can have a solution, because we can either explore this side and get stuck here, because we cannot cross this barrier. We cannot visit the same cell twice. So this has become like a barrier now. So if you go left, we'll remain stuck here. We can explore this nicely, but we cannot ever come back to the right side. And if you go to the right side, the same problem. We can explore all these cells, but we cannot ever come to the left side. So the moment we have a condition like this, where we are hitting an edge like this, we are splitting this into 2 parts. Another thing to be a little bit careful about, so this, not to get biased by this diagram. So here it looks like it goes forward and then hits something. So which means you might want to, if you just get biased by this diagram, you may think that I have to check the previous step to see where I'm coming from and to see if I'm sort of hitting the edge head on. That is not the case. Even if we start something like this, let us say we come like this, and we happen to explore this cell, we would still hit the splitting scenario. So I'll call this the splitting scenario. Even if we come like this and then take a left turn immediately and come to this cell, we have split the grid into 2 parts, and both parts cannot be visited anymore. So yeah, so it not come all the way like this, as a straight line and then hit the edge. It can come like this and just hit the edge. And I'll show that in the code as well. Although that code looks very messy because there are just too many Boolean expressions. I think it is best understood in one's own quiet time, but I'll still show the code anyway. So that is optimization 3. So I will call this the splitting case, the case of splitting the board into 2 partitions where we cannot go from one partition to another partition. So let us see the code. So this is the split occurs function. Given a cell that we are about to visit, or the cell that we will visit. So the input here is the scratch board that contains the visits that have happened so far, and this cell we want to visit. This is that input ing. And we will make tests for hitting top edge, bottom edge, left edge, right edge. Actually, this comment is not accurate. So path hits top edge and creates a split. So that's what we're testing here. And same thing here, and so on. I'll just yeah. And same thing here as well, and same thing here as well. I'll not edit that right now. So I'll just show maybe 2 examples. Just walk carefully through 2 examples. I think that would be enough illustration in terms of code. So we want to check that the path hits the top edge and creates 2 partitions. So how do we do that? I equals 0, meaning the cell that we want to visit is on the top row. Obviously, because we are trying to, if we hit one of these cells, then we have a split. So I equals 0, j not equals 0. We don't want to count a scenario where we are hitting this, because that will not create a split. It still leaves one whole region on the right hand side. That is j not equal to 0, and similarly j not equal to n minus 1. So when we're hitting the top edge, we don't care about this column and this column. So the hit has to be in one of the interior edge cells, I would say, not the corner edge cells. So that explains this. Picks the right column and the right row to check the hit. And then, and this is the interesting part, if ai plus 1 j is visited, means if this is visited, we're making sure this cell is visited. And aij minus 1, which is this one on the left side. So this is the cell we want to visit. We want making sure that this is visited. We're making sure this is free. We're making sure this is free. So these conditions hold good. It means we've created a split. Okay? It may take a while to really convince yourself, but you can like try out different cases and see it really is like that. So if this cell is visited, this cell is free, this cell is free, and if we end up visiting this cell, then we would have created a split successfully. Okay, one more example. So path hits the left edge. Let us try this. Okay, and okay, maybe this one. Path hits the right edge because this side of the board is cleaner. This side of the grid is cleaner. So let us say this path doesn't go all the way up, but at this location, we're trying to explore what happens if we hit this. So we have to check now that this cell is occupied, this cell has been visited, this cell is free, and this cell is free. So in that case, if we visit this cell, we would again create a split. So it would split the board into a roughly upper half and a roughly lower half. And we cannot go from one side to the other because there will be barrier in between. So path hits the right edge. Let us see. J equals n minus 1. So the column we want to visit is on the right edge. And then I not equals to 0, which means we are not at the top row. We are not at the bottom row. Those are checked here. I not equal to 0. I not equal to n minus 1. And then we want to make sure that this cell is, this cell is visited, the one before the cell that we want to visit. So that is aij minus 1. So the cell we want to visit is aij, so aij minus 1. And we want to make sure that this is free and this is free. Those are the other 2 conditions. So like that, we have 4 conditions for hitting the 4 edges and creating splits. So this is one thing we'll check every time we enter this function. So every time solve is being asked to visit a cell, we will check that if a split occurs, we return, because we know after that we cannot solve this problem. We cannot get a path that solves the problem. So we'll return. Another such interesting case is optimization 4, which is what you can see here as the loop occurs. And let us see that. Optimization 4 is something like this, and this might remind you of the snake game that we used to play on mobile phones and other video games. So if this path ends up touching itself like this, then we would create an interior region and an exterior region. And again, we cannot go from, if we choose to go interior after this, we cannot ever come out because this whole thing is looped. So what do we need to check to detect whether there's a loop or not? And this is also a very interesting case. The first thing we will check that we are not at the edges. We really want to make sure that we are hitting the path itself in an interior place, because let us say we go like this, and we hit this here. That is not a problem at all, because we don't have any exterior then. We have a lot of interior. We are not necessarily creating 2 halves or two disjoint regions. But if we end up hitting the path in an interior cell, then we would have created an interior region and an exterior region. So let us see how to test that. So the first line of code here is just, so this is basically big Boolean expression that is doing all the checks and returning true or false in the end. The previous code also was similar. Loop occurs, this will tell us whether a loop has occurred, loop will occur or not by visiting the current cell. So that's what this is saying. The path is not touching the edges, so I not equal to 0, I not equal to the last row, j not equal to the first column, j not equal to the last column. So we're not at the edges. That's done. If this is satisfied, then there are two possible ways to create a loop. One is there is a horizontal gap. There's only one cell is there, and there is a cell. This cell is visited. This cell is visited. This is the cell we want to visit. So if you make this move, we would have made a loop where this portion is horizontal. So roughly, yeah. So this is not exactly a very correct language. It's more like the slope here is horizontal. I mean, I think that is more accurate way of describing that. We're basically creating a loop, but at the point of loop, we have a horizontal slope. So how do we test for that? We have to make sure that this cell is visited, the right side cell is visited, and the middle cell is free, and that is what we are going to consume now. I think that is all we need. Let us take a look. Is that all we need? Why do I have so many conditions here? Let's see. Maybe I've forgotten something. So a path closes a horizontal gap to create a loop. And what are we testing? So let us take this case itself. This is our aij, wherever you're seeing this arrowhead. So this says aij minus 1, which means this cell is visited, right? And aij plus 1, yeah, this cell is visited. Yeah, I forgot two other conditions. That's what I was worrying about, that I must have forgotten something. This is saying that this cell is free. So these two cells are visited and these two cells are free, because we have an exterior region and an interior region of unvisited cells. So that is being tested here. And again, this requires us spending some time and convincing yourself. I don't have a very airtight, rigorous argument like why this expression is correct, but it is quite intuitive to me that it has to be so. I hope it is to you as well. But if you know a very airtight, rigorous argument that why this expression is definitely the correct expression, let me know. So once again, this is saying that this cell is visited and this cell is visited, and this expression here is saying that this cell is not visited, this cell is not visited. In such a case, if we end up occupying this cell, we would have created an interior region and an exterior region. And we will definitely have a interior region because there's only one path. It's a one continuous path that is looping, which is roaming around here. And if we end up touching itself, we just have a loop in that case. So it's quite intuitive to me. Maybe there's a way to very rigorously also explain it without using any visual aid, but I've not spent the time to do that. And similarly, path closes a vertical gap, symmetrical. So it's just a symmetrical case. So we saw how we can go like this, or not really like this. Yeah, I think it is like this. Okay, the exact thing to say would be this cell is occupied, this cell is occupied, this is free, and we somehow come here and stop here. Yes, which means we are definitely approaching from either from the left side or from the right side, because these two cells are free, right? And that would create a loop. And similarly, we can have a case where we say end up hitting this from here, from the bottom. So that would be creating a loop where at the point of impact, we have a vertical slope. So that is this thing. It's a symmetrical code. Not much has changed, except for the I and j, the way we are using this -1 on I and j rows and columns. So that is the fourth optimization technique. So that's what we're seeing here. Optimization technique 1 is something I have not discussed and not really relevant for this problem, but we will see that when we go through this book in a more systematic way. So after doing all this, split occurs, loop occurs, and I'm testing it here. If a loop has occurred, if a loop would occur, not really loop has occurred. If it is checking whether loop has occurred, because we have already come. The act of entering this function itself is visiting that cell I and j. So this is basically checking whether a loop has occurred, and if this loop has occurred, there's no point in continuing further. We abandon the search, the deeper search, and return. And with all these pruning techniques implemented, this code was taking 1.3 seconds to search for 88418 paths, and that would be the case where the input is all question mark. So if everything is question mark, meaning we will end up searching all the paths. It was taking 1.3 seconds, which is not good enough to pass the time limit in the CSES online judge. And then I took inspiration from other examples. Jay was also very nice to share his code with me. His code was, in fact, completing in less than 1 second. And I was just checking for differences, like line by line, what is different and how can I make it fit within 1 second. And let me show you some of the things I learned while doing that. Here it is. Okay, maybe I can expand this. So the problem is clear. So I'll just show both the code side by side. Here it is. So this is the this has all the, on the left side we have a code which has got all the pruning techniques implemented, but the micro optimizations are not implemented. On the right hand side we have the micro optimizations implemented, and I'll show you how tiny differences in the C++ code can start improving optimization. So the first thing I tried, which was not helpful, is make this inline. So basically add inline here, hoping that the compiler will just push this whole function call into this function, and there will be no literal function calls in the CPU. So, but that did not make any difference. And I was testing this on my local Mac system with CLang compiler, so I was not seeing any difference with the CLang compiler. Maybe it will help in other compilers, and CSES uses the G++ compiler. But I'm just explaining my experience trying to improve the performance on my local system, and then I submitted it to the CSES online judge. Okay, so inline did not make any difference. So this is the first optimization that did make a difference. So we started with 1.3 seconds. What I did was move this entire thing. I inlined it myself. So instead of, when I put inline, the compiler did not help me with the performance. So I just copy pasted these two expressions and put it inside the code. So you can see this whole thing has gone as an if statement here. And if this is hit, which is the split logic, split detection logic, I'm abandoning the search further. Similarly, the loop occurs code has gone here. It has basically become part of the solve function, and there is no separate function. So that we have reduced some function calls, and that does make a difference. I go from 1.3 seconds to 1.1 seconds. Tiny bit of improvement, but not good enough to pass the CSES tests yet. The next thing I do, okay, so if you see here, yes, here, I'm trying to do something like this. I call this the elegant recursion, where I do the minimum possible thing in the current level and just call the solve function and let it figure out with the edge cases and everything. So here, even though I know that this I minus 1 may be negative, I'm still calling the solve function. And make the child call, figure it out. If it is negative, return without doing anything. But that does lead to a large number of extra calls, because I could have taken that decision here itself, that I minus 1 is going to be negative, and there's no point in going one level deep. In most problems, it does not make a difference, but in problems like this, where there is very tight time constraint, it can make a difference. So if I can avoid those extra calls and take that decision one level up, and don't even make this call with the illegal value of I or illegal value of j, that would be good. So that's what I'm doing here. Other thing, same thing I'm doing for this one too. So if I already can see it here, that the next cell I will visit is visited, then I will not even call the solve function. So what I've done is I moved this check from the child call in the call stack to the parent caller. So here you can see, before I call the solve function, I'm checking carefully that it's a good call to make. So I'm treating every call as very expensive here, and I'm trying to reduce the number of calls. I've become overcautious, and I'm checking that if I is greater than 0 and the cell I'm about to visit is not visited, only then pay the price of making a function call. And with this optimization, I go from 1.1 second to 0.9 seconds. So with these two optimizations, it is enough to pass the tests on the CSES website. And this one, and I saw that Jai's code was still running twice as fast as mine when I was doing it on CLang, and I was curious what is making the difference after a lot of digging and trying to make changes to the code so that both code look very alike. Both the programs look very alike. I realized that I was using a string here, string path, and Jai was using a character array path, and that seemed to make a lot of difference. So in my CLang compiler on my local system, I was going from 0.9 seconds to 0.6 seconds. So I think the string versus character makes more of an impact with C-line compiler that I have on my system. But on the online jet, it did not make so much of a difference, but only a little bit of difference. It went from 0.9 seconds to 0.8 seconds. And this I found a bit surprising. So the string does seem to have a good deal of overhead. So what is the operation that we do? We only do one single operation. If you see that, we just find out, we just look up like one of the moves from this string. And let me show that place. Here it is. So we pick up the move, the next move, so that we can do this matching, whether the question mark is allowed or U is allowed. So that move is, that code is same here, except that this is a string lookup. We're indexing into a string. Here we're indexing into a char array. And this little thing also brought a significant speed up. Okay, so there's a question, there's a comment by Traxxas, char path n times n minus 1. The minus 1 should not be there. You need space for 49 characters. Yes, you are right. So there's a mistake. You are indeed right, because when we do, yes, I think you are right. I will double check that. I think it should be easy to check from the CPP reference website. But yeah, since we're using a char array, there's a very good chance it needs that extra cell for /0. So thank you, Traxxas, for sharing that. I will just check the C in documentation once and fix this code. Okay. Yes, so with all these optimizations, this program fits within the 1 second time limit, and that's how we solve this problem. So in a sense, to do a quick recap, this itself, I think the code on the left side is a good solution. On the right side, what we have are just micro optimizations to make the code fit within that time constraint.